Hello everybody, good morning. I'm going to watch this video of hythloday from about a week ago that I only just watched last night. And then I was going to reply to it last night, but he mentioned another video that I watched first.
Oh, good to hear from you again. Don't see much of you these days. I appreciate you're busy with your new contracting business computing career.
Yes, but most of the time has just been working on my own projects and things, the kind of stuff that I think I need to get it going. I hopefully am going to sign an agreement today for a 3-month contract that'll take me through the winter, which will be nice.
Okay, it's going well. Thanks for the video response. You prompted me to watch a video I saw many months ago titled "The World as a Hologram." In this video, there's also the world of a hologram by Suskind, but this one is by a guy called Raphael Busso, I think the name is.
So that's the video I'd watch, and I have to admit, I didn't take a lot of specifics that he was saying from it. I'm sure I missed points he was making, but I saw the general gist.
I'll attach the link, and I think it's very informative as to the nature of the holographic principle and the assumptions that lead to the conclusion. Whilst not explicitly detailing the math, it is enough for me to realize and understand that the holographic principle is a hoax. The world as a hologram is a hoax.
Now, this is the second time I've watched this video. One reason I'm watching it again and doing this live kind of responses, because I'm not really sure where you're getting at now. In a second, remember you say, at least in the popularization of it. So, yeah, to me, a hologram is a thing, It's so saying the universe is a hologram is drawing a metaphor to like a holographic sticker. Right, when you look at a holographic sticker up close, not from the just reconnect.
We know a strong economy depends on a good education. Someone should tell Governor Paul LePage. LePage tried eliminating Head Start programs.
It said lost connection to the server, and then it fed me this ad trying to get me to vote for Governor LePage.
Can't afford it. Tough luck. No wonder Maine is 47th in economic growth, and 40,000 Mainers are unemployed. It's time for Mike Mishu, a commitment to education and jobs, and a detailed plan to get Maine moving again.
In the sense that, in the way that it's sold to us at the most common lay level.
Okay, you've seen the Suskind stuff. I think the most lay level that he does is you have a holographic sticker. If you look really closely at it, I mean, don't pull back and look at the hologram, the holographic projection, but you look at the sticker, you see it's just a bunch of, it looks like noise. Now, obviously, sometimes you can see an arc or pattern in it, but, it's not really clear what image it's of. And this comes from the fact that you're taking 3-dimensional data and you're encoding it in a 2-dimensional space, which is something we do all the time. A computer memory, is really just a 1-dimensional string of numbers, but we have to have 2-dimensional and 3-dimensional arrays, so we decide, well, hey, at this point we'll choose a finite section of that and we'll call those the rows, and then we could stack the rows. And this is basically what you have to do. You could take a finite amount of 3 space and encode it on a finite, but in a sense larger amount of 2 space, right? larger than a two-dimensional information would take. You need the extra dimension to have room, and you also need to take a finite set of what you're going to encode. And those happen to be, doable. And I think the holographic universe is just taking this example, but more from a hologram, where you have a two-dimensional sticker, and what it is that every point on that sticker, I mean, basically you could think of a hologram as, those old things where, you put it like this and you see one image, you put it like that and you see another image, and in the old ones you can look at the side and you can make one of these even with strips of pretty big paper, right? You have your canvas or whatever here, and you build all these ridges, and on this side of all the little ridges you put strips from one picture, and on this side you put strips from another picture, and somebody from here sees the one and somebody from here sees the other. A hologram basically works by the same principle, except for you have a little reflective ball there that has more than just two angles. It's got angles from all over, and that's how you have the hologram encoded, right? So it's a way of folding the three-dimensional information onto a two-dimensional surface. And the interesting thing of applying this as an information processing system to me, or a mode of information processing of the universe, is the funny things that have to happen when you encode the data, and sort of the mathematical things of where certain amounts of information become possible or impossible, right? For example, arriving at this surface to volume issue with the black holes and in the general universe, it says something about the fact that the universe is expanding, because if it's a holographic universe, then that means while there can be more and more information in the universe as the surface expands and there's more space to store the hologram, so to speak, the information per unit of space in the volume has to drop. Right, the average information per unit volume, and that would have, and can have interesting physical consequences if it's true. Now, mind you, I think one thing that was good that guy at the UC videos, he was from Lawrence. I think he was from Lawrence National Laboratory. That's what he was kind of talking about, is that you can have you can get a small enough space that never mind, I lost it. What the fuck was I gonna say? It's confusing stuff. I'm sure it'll come to me again.
It's sold to us upon the idea of asking how much information is contained within a particular volume, okay? And this,
I think maybe you're getting ahead of yourself, right? I think that's the weird conclusion.
Seems like a worthy question.
Well, don't get me wrong, though. I think that's the deeper understanding of it. It's this surface to volume issue with information. Oh yeah, I know what the guy was saying. So the point he made that I thought was really good is it's not so much that there's once again we have this meaning like a dark matter or something, and it's describing this phenomenon that we've noticed. Not that there's an ontological interpretation that we can take from it. It has to do with the fact that all this mathematics between looking at this as entropy and information, it generated a one-to-one match. So you can think of entropy and information as the same in the sense that you treat them mathematically exactly as the same.
In this video, you spoke about fields, and I'm glad to hear that you also just think as fields as numbers in space. The problem is that I have is that as numbers in space, what you understand it to be is an entirely abstract idea, like a mathematical line or a mathematical surface. Whereas with a mathematical line, and I'm going on a bit of a tangent to address a little discussion about fields here. The point is the problematic and it's because it is mentioned in the video, and I've indexed it and made many timestamps in my most recent comments. The implication of fields is infinity, is infinite information, as Raphael Bousseau puts it. As with many other problems that I've made lots of videos and we've talked about in the past. So let me talk about a singular function, a mathematical line which represents a function. You have the x-axis, and then you have the y-axis as the answer output. So for some particular x, you can move up and you get one singular answer. In fact, lines which provide two answers, say a curve like this, would give two answers for one particular x value. And you'll understand now that why we describe the ones that don't give two particular answers as functions, and their importance, because they in a way conserve information in the way that we constrain, you know, always knowing where we came from and where we go to. So,
is that right? I mean, if I have, let's say I have a parabola, and, you know, I rotate it so that it's, you know, x equals y squared, so it's y equals square root of x, or whatever it would be, however that would work out. Or if I screwed it up, whatever, you know, you rotate that's still a function, isn't it? And I'm not saying that it is. I'm asking, isn't that still a function? A function doesn't just have to have just one output, does it really? I could be biased by, you know, some more generalized view, or the fact that I use the word function for all these decades in this programming, where it's like anything that has inputs and outputs. But okay, go ahead.
It's easy for me to represent this singular dimensional function pictorially with a line.
I love that you're doing the axes with your hand. I can see what you're projecting. It's like bzzz. It's like you're using an invisible, you know, modern Minority Report type of computer, because I can see that works for me. You do that, and bzzz, the coordinate system's up there. Okay, I see it all.
You can also consider a
rotated
function, which outputs a singular answer in a third axis.
Right.
And this will have a place upon a certain, and we'll plot a surface.
And this is how I think about it.
So any particular point on the plane will be able to map up to a surface. And
even though I tried to pick a nit in mathematics that you probably are more familiar with than me, I should say, no, this is exactly, I've thought this through exactly this way before, and when I was younger and since then, you know, and it's always very interesting to me the way we, on a graph, you assume what the input and output is, and the weird things that happen when you want to use the other one as the input or the output, which I run into in computer science, and it can get confusing. Like, wait, which is the here and the there, you know?
Yield a y answer, if you like.
Got it.
So that's two-dimensional. That is representable in a visual.
But personally, I like the z going up. I like z going up. I never understood why they would have x and z and then y still go. It's a mathematics thing.
Sense. When you move to 3 dimensions, we've lost. We always use an axis to output the answer, but now one of the dimensions is utilizing the answer. So we have a function of 3-dimensional space where there is an answer, but I can't represent all the dimensional axes pictorially and the answer axes, because we are limited to 3-dimensional space.
Right. See, I watched this the first time, but, you know, it's interesting to slow and just actually respond as the video plays. I think it's me to watch it better. Okay, totally. Yes, that's what I think what's going on with fields. So which is why really every field is a dimension, because if you could visualize things in 4 dimensions better, you know, you just would. And frankly, I think it's pretty good visualization, a fair visualization, to have these little vectors at points in space. You know, you can picture that. You know, you can picture a surface with the gradients, you know, at every point. You know, it looks like water rushing over rocks. It's like, it's not so much where it is, but kind of where it's going, and that's what the fields are. But I agree with you if what you're saying is that really if we had more spatial dimensions that we could visualize, we just create another axis, and that in essence we have created another axis, and so the fields are treated as other dimensions in this mathematical free variable sense, orthogonal free axes. And then the fact that we visualize it one way, we should not put ontological meaning into the fact that we can't directly visualize a 4-dimensional space as spread out, and we have to stack it up. We have to put this 4 and 5 and 6-dimensional information into a 3-dimensional appearance of the world. Now, I'm going to pause here and just make sure that the audio, before I do much more, is even, because I have about 17 minutes here. Would hate to do very long without being able to hear your audio or anything. So, okay, I'll be right back. Oops.
It's a special kind of function, a 3-dimensional function, where the answer is dependent upon the location in space.
We're talking about the functions.
Okay, so let's get back.
When you get where there's 3 inputs.
The premise is to consider, and what is sold to the layperson is to consider how much information can fit in a volume. And they say that rather perversely, rather unintuitively, rather paradoxically, that contrary to how you might imagine, that surely that it would be dependent upon the actual volume itself. If you imagined this as a cubic array of rooms, that you...
Oh, that's right. No, we're talking about the volume, the amount of information a volume can contain. Okay.
Clearly, if a piece of information was placed in each room, the information is dependent upon the volume. And they go, but it turns out it's not. But how they try to convince you, Raphael, Professor Rousseau does in this video, explaining the assumptions, what is actually done is something entirely different. What they say is built upon, well, there's a few coincidental things, but it's largely built upon the conception of black holes, you see. Now, the idea is...
I've become a big fan of your demonstrations, and I just realized that your cube was made out of straws. Awesome.
Think about black holes. Is when you consider the event horizon of a black hole, that it's never fixed, and yet we want to...
Look, you have a black hole right there, and it's yellow, so I think calling Stizor black holes are yellow.
Think about information in a fixed volume. If we have a black hole this size, when every time I consider another piece of information going into the black hole, in terms of its event horizon, I can't help but think of it expanding. It's an intractable problem. I can't fix what I want to fix.
Okay, But it does get bigger because that bit of information has energy or mass, which causes the mass of the black hole to become greater, which means that the event horizon does expand, right?
So, in this video,
and I think this is kind of the argument. It's sort of like the black hole gets just enough bigger to encode the information that's fallen into it. But there's a bigger volume that in some sense ought to be able to store extra information. But for extra information to get in there, it would have to go through the event horizon, and it would always go by this much. So it's always going to get more volume out of it than it needs to encode the information. Something like that.
Russo explains that we change the problem from considering a fixed volume in space to imagining the size of and quantity of energy that defines and fits a certain volume of a black hole. And it's not really the volume of space that we're considering packing information in here, you understand? Because bio-world discussions aside, for the longest while it's been held that as you pass the event horizon, nothing particularly, it's either if it's large enough or small enough, you can actually pass an event horizon in a spaceship without actually noticing anything physically different. This being the case, you understand that the question of volume, the nature of space.
I'm just distracted by the fact that I noticed this thing showing pictures. I'm not sure if I want all my pictures shown, but isn't that dog cute? Lily. So cute. I had to power that up. I'm going to have to go and probably finish this later in a minute because I have some stuff I've got to do.
Discrete, continuous, having dimensional length specifications.
Yeah, I got my pink glasses on. I probably don't need those. Not reading.
There's nothing to do with the dimension of a black hole. Because the thing we want to fix, as you pass through, causes it to expand. This is... So it makes no sense. I mean, it's an interesting mathematical puzzle to say how much energy is contained within a particular volume of a event horizon.
See, I just want to stop for a second. You said energy, and I think this is really what they're getting to, is that, you know, like he was talking about, the black hole expands, and it can only expand. Now, we have the Hawking radiation, so they can't evaporate, but in the sense of this event horizon, since stuff can't escape, it only expands, and that's just like entropy. And just like entropy, it always has to get greater, and yet we see things like living systems reducing entropy all the time. And it seems related to the fact that they could process energy as information, and that in that sense energy is kind of translatable into information. And then you have information science and the study of like quantum entropy and the conservation of energy and how they all relate. And it turns out the math to describe how the information flow works matches the mathematics that describe how the energy work, and they're translatable. And it's kind of like, oh yeah, you can look at the world as information, you know. And it's not that the world is just information necessarily, but it's a fascinating thing. And when you think about the deeper questions of natural philosophy, coming back to regular philosophy and how humans exist in this world, it's pretty interesting if we come back to information as somehow being something that you can quantify, when we thought information was this abstract thing that didn't even exist in the material world. It's metaphysical, the world of forms and blah blah blah, right? No, it's all just a part of physics. And so we're kind of seeing where information is related to physics, and entropy represents in that if you apply the similarity as a metaphor, entropy is information that you don't know, and when you gather information, you reduce entropy.
Professor Bousseau also says that, you know, that it's the idea of a volume, the volume of a black hole is undefined, not very well defined. That's right, what he says. And so this feature alone.
I must have missed that. He was saying that the black hole, in a sense, is the simplest physical object. But I mean, I could think of where it's hard to define. Like, for example, what's the volume of space inside the black hole? The space is distorted theoretically by general relativity. So, but in a sense, the event horizon is probably the most well-defined and perfect shape we know of.
Points as well to it not being a readily applicable analogy in which to address our problem and our foundational problem and question about how much information is in space and what the nature of space is. So in this lecture, he brings together essentially Einstein's general theory of relativity, which assumes continuous space and the infinities of the singularities of black holes and etc., which are all questionable in themselves. It's clear to everybody, I think, that general relativity is flawed, because theories that generate infinities allow for almost anything to happen.
Right, and Hawking was siding with the general relativity side and then changed his mind. Because, yeah, it seems like the problem is that we can't explain quantum gravity. Right? It's not that we can't explain a relativism. It's clear that relativism is ignoring a big fundamental part of the picture physically, and that to me it seems clear that quantum mechanics is what needs to be modified, and relativity is sort of a standalone thing, like a certain mathematical operation or practice that is useful but needs to be applied to something else. So the ideas of general relativity need to be absorbed by quantum mechanics, really. That's the promising direction, as opposed to the other way around.
Theories that generate infinities are deemed to be flawed.
But in the end, you know, you'll end up with a system that you could say was relativity adapted to quantum mechanics, or quantum mechanics adapted to relativity, and in reality it's going to be a new theory that's related to other theories historically, but not those other historical theories.
General relativity doesn't fit quantum mechanics, so that implies one or at least the other is wrong, and given the infinities of general relativity and all common sense, it seems clear to me that general relativity is wrong.
I think, you know, the standard understanding is that they're both wrong in some sense, and any replacement theory will be wrong in some sense, but we're narrowing the phenomena that can't be explained when we come up with an improved theory. So I think it's clear that both theories are subject to improvement, and really it should have been clear in classical mechanics that was the case. Right? They're fooling themselves in this ancient search for the one true answer and thinking that they got it. In reality, it's an evolving answer, and there is more and more information for us to get. And even if there's a finite amount of information in the universe, we are a very tiny, tiny, tiny subset, you know, more finite. And, you know, for an individual mind, there is an infinite amount of information that can be extracted from something.
Though it is the best description we have, and is creditable, and is a beautiful mathematically geometric insight, no doubt. So what he's doing is actually changing the problem from the volume, the fixed square volume perhaps, to, and it's rather doesn't matter whether the shape of it is circular or square, but once it changes the dynamics of a question to the black hole question, the initial question is completely lost. Once the black hole expands beyond the size of the first considered volume, and this question is posed, clearly the original volume still exists within this volume, and we're actually stating nothing about the information content of this mathematical volume, which was the original question. Okay.
Dog moments. Okay, I'm gonna take a break. I gotta do some other stuff. I'll be back. This is about. See, this is where I need my glasses. This is about 14 minutes in. Okay.